All right, time for parametric equations part 3. Anyway, so yes, as you can tell from this slide, I had my original video, then I made part 2, and now part 3 to cover all the introductory stuff about parametric equations. Okay, so I just put this slide up there for continuity between the videos, and here's the first problem that I want to do in this video. So it says, give the path of parametric equations given by x is 2 sine theta, y is 3 cosine theta, and theta is restricted between 0 and 2 pi. Now, at this point, and now that we've done a few examples, you might say, well, so here the parameter is t, right? You get x and y, which is some point on graph paper, or so some point in two-dimensional space. And you get that from this third thing, t, all right? But the parameter can be any other thing, okay? It could be an angle, but it's the same idea, is you get x and y from some other thing, okay? All right, that's what parametric equations are. You get x and y from something else, right? Independently, we get x and y from t, or we get x and y from theta. And beyond that, it's just calculations. All right. So, and one comment before we do this one. This time, theta is the parameter. All right. When we talk about having parametric equations, there is a parameter, and this time it's theta. And some of our other problems, as I mentioned, it's t. All right, but there's just a third thing that x and y depend on. So here on this one, it just says give the path, because that's the part I want to focus on about this one that I think distinguishes it from some of the others that we've done at this point. Now, there is another one that I did that I said, remember this one? This looks kind of like this one, where I said, in order to give the path, in order to eliminate t, probably this identity would become necessary, okay? Because I've got x and y independently in terms of sine and cosine. This would bring them together. So still, I think that same identity is going to be useful in this one. So maybe we're not sure how yet, but given that I have x and y expressed in terms of sine and cosine, then I'll say, well, it's like I'm thinking that this will become relevant or useful. The fact that sine squared of theta plus cosine squared of theta is 1. It's a universal identity. All right, so let's see if we can work these around to use that. How about this? Let's solve both of these in terms of sine and cosine. With this first one, this would say x over 2 is sine theta. And this one would say y over 3 is cosine theta, okay? All right, so that takes me from here to here. Then for these, given that I ultimately think that that's what I need to eliminate the parameter, the path is just information about x and y. We lose the information about the parameter. Then I'll square both sides of each of these equations. If I did that, 1, that would be something that's allowable, and 2, it would introduce this possibly, okay? So say I do that. Say I take what I have at this point and I square both sides. Then I'll get x squared over 4 is equal to sine squared. And then from this one, y squared over 9 is cosine squared. Okay, now what about this? Well, at this point, I can use that identity, okay? So it's like, look, sine squared of theta plus cosine squared of theta is 1. Okay, that's the way it works, right? And this time, I've got sine squared and cosine squared. If I add these together, I'll get 1. But they're linked with these other things. So if I add these together, I'll get 1. All right? Now from this point, sine squared plus cosine squared is 1. Therefore, x squared over 4 plus y squared over 9 is also 1. So this would be my path right here. Okay? Now, what is that path, though? I mean, the idea is that we might recognize this so that if we could graph it, if we needed to. This is an elliptical path. Okay, that's the equation of an ellipse. Now, real quick, let's say that we have a rough notion of an ellipse. All right, now I know that you might not remember every detail that you ever learned about an ellipse, but you should roughly know what one is. Take a circle, make it a little wider or taller, and you get an ellipse. But in order to sketch this, like we're required to do on most of the problems that we work these days, I'll find out where does this particular ellipse hit the x and the y axis. Okay, so like what's the x-intercept of this ellipse? Like, now, even if you didn't know it's an ellipse at this point, can you tell me where this hits the x-axis? Well, you would let y be 0, and it would say x squared over 4 is 1. It would say x squared equals 4, so x would be 2 and negative 2. Okay? And where does this ellipse hit the y-axis? Well, okay, so on the y-axis, x is 0, so we 0 out the x. It says y squared over 9 is 1, or y squared equals 9. Or y equals 3 or negative 3. So it's an ellipse where the major axis or the longer axis is vertical. All right. So there's your path for this one, is this elliptical path. Hitting the x-axis at 2 and negative 2, and the y-axis at 3 and negative 3. Okay. So you might not remember everything about an ellipse, but there it is for this one. Okay, all right, now maybe at this point, let's get a few points along with the parameter that goes with them. Okay, so where are we when theta is 0? What's sine of 0? It's 0. What's cosine of 0? It's 1. So we're going to get that y is 3 times 1 and x is 0. So let's do a little bit of that and we'll put it all together right here. All right, so here it goes. There's my table. My parameter is theta, and I'm going to calculate x and y. I'm going to put all that on this picture and give you the path and the direction all in one. I know the path is elliptical already, but let's find some points in terms of theta, and we'll see how it traces over this curve. Okay, so theta was running from 0 to 2 pi. So 0, how are we going to get from 0 to 2 pi? How about 0 pi over 2 pi, 3 pi over 2, 2 pi. Those are some of many, many points you could choose to make your graph. So again, what if theta is 0? What's x and y? 0 and 3. Okay, and what about pi over 2? What's sine pi over 2? It's 1. 2 times 1. What's cosine pi over 2? 0. So I'll get 2 and 0. Okay, so pi, all right. Now I'll just do the math on the rest of them, but I'll get 0 and negative 3. Okay. For 3 pi over 2, I'll get negative 2 and 0. And for 2 pi, I'll get 0 and 3. So it's going to, that parameter interval for those equations will take you all the way around. Okay. You'll start here. 0, 3. You'll start here when theta is 0. And then you'll be here when theta is pi over 2. And then you'll be here when theta is pi. So I see as the parameter theta increases, it's taking me like that. Okay, keep going. Here, theta 3 pi over 2. Okay. And then back to here when theta is 2 pi. Okay. So it's taking me clockwise around this ellipse. Okay, so those equations, this parameter interval, have an elliptical path like that, and will take me clockwise around it. Okay, so that's what the information I can get out of that one. Now, it may bother you that when I did this other one that was a semicircular path, that the t, and I said, well, t was the parameter. You can think of that like time. And here, I guess theta is an angle, but it plays the same role as t. It just tracks the location of my points, all right? It's still true that whatever you think of that parameter to be, it's just a number, and it gives you x and y. And as that theta, that number, that parameter gets bigger, your points track in a certain direction, hence the arrows, okay? So it might seem a little more awkward that I called it theta instead of t, but that's, you know, it's not me. That's just the way that people use this. They could call that parameter, you got the whole alphabet, you call it whatever you want, okay? But I need you to see this and see that, all right, I understand it's elliptical. I understand we're moving clockwise. I can see the numbers on the table and so on, and it's all consistent in this picture. Okay, so there's another example done. Let's look at something called a cycloid, okay? So a cycloid is, I guess with respect to what we've been talking about in the other examples, maybe a more complicated thing. We might have to invest a little bit more time on this in the beginning to understand what it is, but I think once we understand it and we're familiar with this scenario, it will be fairly easy, okay? So here's what a cycloid is. Imagine that you had a wheel rolling to the right along the x-axis, okay? And we're going to observe a fixed point on the wheel. So there's a point on the wheel that's fixed and isolated on the wheel, and it doesn't move. But as the wheel rolls, that fixed point moves through space, okay? Now, the path of the fixed point through space as the wheel rolls is here in red. And that path in red is called a cycloid. And you can imagine it like if this wheel rolled and you watched that point as the wheel rolled, then it would move up and back to the bottom, and as the wheel kept rolling up again and then back to the bottom, and it would just repeat. These arcs are called cycloidal arcs. And as this wheel rolled, it would just go up and down, okay? All right, now that's what a cycloid is. Okay, that thing in red, you're looking at it. Okay, that's the concept of it. At least, I don't know at this moment that I'm making this video, but if you go to Wikipedia and type in cycloid, there's a really good animation of this, where you can see the wheel actually rolling and see the point move, and it just traces out these arcs, okay? That's what a cycloid is. Now, so let's talk about the parametric equations for it, all right? Because it turns out that we can give the path of a cycloid, that curve there in red, we can give that parametric equations, okay? So here's how we define everything. This angle right there is the angle of the rotation of the wheel. When theta is 0, our fixed point is at the bottom. So with the point being right there, it looks like the wheel may have rolled such that that angle opened up to be 45 degrees or so. Okay? Or sorry, 90 degrees, pardon me. All right, so roughly that's what we're seeing, like to get from here to there. But when theta is equal to 0, it's at the bottom. Okay? When the wheel starts, say the wheel starts right there, then the point you're observing is at the bottom, okay? As the wheel rolled forward a little bit, now that point's here. Okay, so that's what the angle theta is. The location of this point, in terms of its x and y coordinates, that point right there, is given as a function of that angle, okay? Here it is, x is r times theta minus sine theta, and y is r times 1 minus cosine theta. Those are parametric equations for that arc, or these arcs, okay? All right, so anyway, what about r? R is the radius of the wheel. So you can find the x and y coordinates for all the points there from theta, from knowing the angular rotation of the wheel, okay? All right, so that's what a cycloid is. Now, let's take an example where I think if we got that out of the way, if you're okay with this first slide, if you see what I'm talking about there, then I think that would make this example pretty easy, okay? It says sketch the graph of x is equal to 9 times theta minus sine theta, and y is equal to 9 times 1 minus cosine theta. Well, that's just like this thing right here. That's the exact form. It's just that r is given to be 9, okay? So this would be a cycloid. Yeah, do we recognize it? Yeah, it's on the other slide. Made by a wheel that has a radius of 9, okay? So if a wheel of radius 9 was rolling and we were tracking the movement of a fixed point on the wheel, it would move through space like that, okay? All right. Now, it says sketch the graph, all right? Now, I know it's a cycloid because that's the form of these equations. And this is what a cycloid looks like, okay? On my other picture, I drew it in red, but I said, yeah, in red there, that's the path this fixed point is going to make as you watch it on the wheel as the wheel rolls, okay? So there, I just reproduced that. But I thought, you know, for you to recognize a graph, you might need to identify some key points, okay? So here goes. What if theta is 0? What do you get out of that? What's x and y, okay? Well, we'll do the math. We'll put 0 in for theta, for x and y, and you'll get 0 and 0. And I said, what if theta is pi? Why did I choose that point? Well, I'm thinking of it like this. When the wheel is here, and the point is at the bottom of the wheel, okay? This fixed point that we're watching is down there. Okay, and theta is 0. So yeah, we're getting this point right there, 0, 0. And theta is 0 when the wheel has yet to roll, the x and y coordinates of the point is going to be 0 and 0. And then pi, well, that's the wheel rolling 180 degrees, okay? What's that mean? Can you imagine this wheel right here? But it's rolled such that that angle has opened up 180 degrees. Well, that point that was at the bottom right here would now be at the top. That would be right there, okay? So that would be that the point is at 9 pi and 18. That's 9 pi. That's x. 18. That's y. So that point right there is 9 pi and 18. Okay? All right. I just did the math. There's my equations. I put pi in. I know it's that point, though, at the top of the arc, though, because that's my angular rotation of the wheel. That's 180 degrees right there. Okay. All right. And then I chose 2 pi. Why did I choose that? I think that will give me this one. Because right there, the fixed point starts at the bottom, the wheel rolls, and the point moves through space like that. By the time it gets back to the bottom, the wheel has turned around 360 degrees. So if you put that in, 2 pi for x and y, you get 18 pi for x and 0 for y. That means this point has an x coordinate of 18 pi. All right, so that would give you some scale for it. Now, I think all these numbers are consistent with where we started. Like that one is easy to catch. I mean, what was the radius of the wheel? It was 9. Okay, so this wheel's rolling, okay, and then the point that was at the bottom is now at the top. How high up should that be if the radius of the wheel is 9? Well, that would be the diameter of the wheel. That would be 18 if the radius is 9. All right, so all the numbers, I need you to get to the point where you can see the numbers are all consistent with the equations, with the situation of it. These arcs created by a wheel rolling along, by my numbers, and so on. So we could recognize this graph then, first as a cycloid, and then with the points that I gave you right here. Okay? All right. But, that very heavily hinges on this initial discussion I gave you about what a cycloid is. So if you need to look back at this slide, do it. Make sure you can see why I think the shape is what it is, the points, and so on.